Okay, our next speaker is Chandramouli Chowdhury, and he'll tell us about simplicity of in correlators.
Thank you very much. It's great to be back here after 1.5 years. So I'll say about some work that has been in progress for some time. It's in collaboration with Arthur Lipstein, Jajime, Ivo Sachs, Pierre Van Hove, and Joe Marshall. Something which should hopefully come out next week, but let's see. Okay, good. So in this conference, we've seen plenty of nice structures in scattering amplitudes, and there's been a lot of emphasis on methods other than Feynman diagrams used for computing scattering amplitudes. And for example, sometimes these methods are motivated by some positivity properties, sometimes by geometry. And as an example, we have the well-known BCFW, soft theorems, and so on. Although not many, we have also seen a few examples from objects apart from scattering amplitudes. For example, we saw in Sid and Paul Heslop's talk about some correlation functions, and also in some other talks on the wave function. And in this particular talk, I'll focus on the observables that you can compute using the wave function, which are often known as the in or cosmological correlators. Okay. Good. So the in correlator is an object which actually was defined in the last talk, and it can be viewed as the following correlation function, where you basically have a state and you just compute some correlators at some given time slice. And it can be defined by the following path integral, which really follows from our QM 101. These objects, psi of phi, these are known as the wave functions, and you can compute them in the path integral formalism. And perturbatively, you can draw Witten diagrams in order to compute them. It's basically what Nima talked about. And at first glance, the correlation function seems more daunting than the wave function, because you have to first compute that, and you have to then perform another path integral. And it actually might be true. So for example, if you actually try to do that at 4 points, you'd find that the 4-point in correlator has the following expansion in perturbation theory, where the tree-level term depends on the tree-level wave function at both 4 and 3 points, and the loop-level term depends on the one-loop wave function and also the tree-level wave functions at higher points. You could have opted for alternative approaches like the Schwinger-Keldysh formalism, but it's not something I'll be discussing now. Good. So let me just recap everything that Nima said in lecture 1 in one slide. So let's see how that goes. So I'll consider massless phi-cube theory in flat space. And the expression for the 3- and 4-point wave function is just given by the following set of integrals. So the 3-point function is just obtained by stitching in what are called bulk-to-boundary propagators. You can think of them as plane waves. And you integrate them from 0 to infinity, because 0 is the point where you're evaluating your correlation function. So that's this object. And the 4-point function has a diagram like this, where apart from these plane waves, you also have an object which is known as the bulk-to-boundary propagator, which almost looks like your standard Feynman propagator, except for a term which is necessary for your boundary conditions. And here you can actually perform the time integrals fairly easily. And you just get the following expressions. And as you can see, they have poles. These are some functions of momentum defined here. And the residues at these poles have physical meanings, which I'm not going to discuss now. And you can also derive some nice recursion formulas for these objects. The only important thing here is that this is, you don't have energy conservation in this. By energy, I simply mean the mod of Ki. Okay. And with this, you can compute the correlation function using the previous formulas. And in this case, it's literally just a sum of these two terms. Okay, good. Now, things would start getting more difficult if you consider something like de Sitter 4. So the example in the previous slide was for flat space. In de Sitter 4, it's almost equivalent to a time-dependent interaction. So you have to almost perform the same integral, but with some factors of t1 and t2 sitting in the denominator. And in this case, you can actually perform this integral easily. It was performed here some time ago. And you have this very nice dialog structure, which we also saw in some other talks. And with this, you can then compute the correlator with a simple replacement of this. From here, you actually notice that even in tree-level correlators, you already start seeing polylogs, which, as you know, for the S matrix, that's not true. So this should tell you that it's more difficult. Good. So as we already saw, these scalar integrals can often be very difficult. And it's much worse in loops. And in fact, we only have very few loop integrals, which are done only in some axisymmetric cases. And in fact, for spinning cases, it's even worse. because we don't have any MHV type computation beyond 4 points, which Suvrat actually did many years ago. And it gets much worse on gravitons, because right now we seem to have 3 different expressions for the graviton correlator, the 4 graviton correlator, and it's not obvious to check if they're all the same. Good. Now, again, all of this progress here, even for spinning theories, have all been for the wave functions. But as we just described, for the in correlator, you have to do one more step. And in the next few slides, I'll hopefully give you something, a slightly new formula where we'll directly compute the in correlator by using Feynman diagrams. Good. Good. So to keep things simple, I'll consider the same theory that Nima talked about a lot, which was scalars in flat space with time-independent couplings. But most of what I'm going to say can be generalized to many other things. So let's just go back to the wave function, which I talked about a few slides ago, without the time-dependent interaction that had the structure. And now I'll just use a different representation for the bulk-to-bulk propagator than what I used before. So it's something which you can write in terms of some integral over sine functions. And performing the integral gives you some expression of this kind, where I simply interchange the order of the 2 integrals and first perform the integrals over T1 and T2. So given the structure, you could say that this looks very similar to an integral over a flat space Feynman propagator. But this guy is the flat space Feynman propagator, and these are some kernels. And was this a coincidence? Turns out in this case it's yes. This was indeed a coincidence. And the structure doesn't quite work in the same way for higher points and loops. And plus, again, this is still the wave function. You again need to compute the in correlator. But turns out, if you actually do that computation, you could write the in correlator in a very similar way, where you take your flat space Feynman propagator, and you perform an integral over the energies with an almost similar kernel. In fact, for this example, the only difference is the factor of p squared in the numerator. But the important thing here is the same kernel works at arbitrary points and arbitrary loops. So if I now wanted to evaluate the in correlator at the next loop, I would have the same kernel, but just put the flat space bubble integrand. Okay. This is in general theory dependent, but I'll not talk about all the generalizations now. Good. So this actually allows us to write down a very nice representation, say for the S channel. As long as you're dealing with, say, 4-point functions, you can use the same kernel here and just sum over all the Feynman diagrams that you would have done in flat space. And notice that energy conservation does exist for these all guys. Where it breaks down is once you integrate over this, but this thing is really your flat space, well-known textbook stuff. Good. So for the T channel, you would have a very similar representation with these labels getting switched, but there's a similar expression. But the nice thing here is it generalizes to higher points, again, in a very simple way. We just, where say you want to do the triangle diagram, you insert the triangle Feynman integral, and then just multiply with some kernels. Good. So the general rule is that you take any Feynman graph you like, and you integrate over the energies by multiplying with some kernel. Okay? And this computes the cosmological correlator, or the in correlator. So for example, if I look at the bubble diagram that I just described, you take your flat space bubble diagram and you attach 2 propagators, which are one-dimensional, only carry energies, and have the structure. And then you can just write this diagrammatic rule for any general graph like this. Okay. Good. So until now, I mostly just talked about theories which are very simple, which was massless theories in flat space or conformally coupled theories in de Sitter. But you could try to also do it for something like massless theories in de Sitter, where you would simply insert some differential operators, and you can think of these as some weight shifting operators at a p-integrand level. Okay. And for other masses in general, these S integrals would have other things, which is still work in progress. Good. You could now ask, what's the use of this? Was this? Did we? I mean, that's often a question. And of course, one use is that we know a lot about flat space loop integrals. That's something people have studied a lot, and of course, we've seen in this conference that's been going on. So you can then use the knowledge of your flat space loop integrals to now compute the in correlator by just integrating over the energy. That step might not often be easy, but it's still better, I think, than what we used to have before. And just to give you an example, the bubble diagram for the NN correlator has the following expression. This is evaluated in something called analytic regularization, which preserves conformal invariance. And as you see, it only has logs. In fact, it has a pi over log, pi times a log. But it's still simpler than what's the wave function coefficient, because that's a dialog. But okay, you could, I mean, depending on how you count the transcendentality, you could, that's either simple or not. But a slightly more non-trivial example is the triangle, where you have this integral representation for the NN correlator, and we expect this to be polylogs, and with similar leading square roots as that of flat space. And for this particular case, the corresponding wave function was actually argued to be elliptic by the following set of authors, but we still don't have an explicit expression for this. Good. So now I'll conclude. I think I'm good. I'm just done on time. Excellent. So, so the summary of the talk is that we obtained an integral representation for NN correlators in terms of flat space Feynman diagrams. And this bypasses the need of computing the wave function coefficients and also avoids any long computation using Schwinger-Keldysh. And in flat space, for example, all these correlators are IR finite and can also be viewed as useful regulators. And such integral representations would now allow us to study cutting rules for NN correlators, which until now I don't think would develop very nicely. And this was all done for scalar theories, but I think what would be really nice is to connect it to spinning theories and also fit in with these BCFW recursions in EDS that were derived many years ago. And then, you know, in terms of future directions, you could ask if this was just a consequence of working in bunch Davies, or does it also work for alpha vacua? And maybe is there something like this for the NN correlator in flat space, like the scattering cross section, where you bypass the need of computing the S matrix? And final, I guess, question which bothers everyone is, does any of this sustain after renormalization? With this, I'll conclude, and thank you.
So could you say a little about how this relates to this in-out formalism that also, you know, doesn't compute the wave function?
Yeah, good. So for this particular theory, like, you know, the massless theory in flat space, wherever I had it, let's say something like this, the in-out formalism would have given you the same answer. In fact, if you use the formulas that are predicted by the in-out formalism, you see this guy, this 1 over p square, if you like, or something like this, is really the in-out correlator. And what the in-out correlator asks you to do is sort of integrate over the energies, and then you can actually perform some variable shifts to get it here. Where I think it starts failing is when you consider something like massless theories in de Sitter, because then in intermediate steps you have IR divergences. So that's something I do not know if the present version of in-out formalism, I think it can't handle.
Can I ask you on these integrals? So the 4-point, the scalar bubble is UV divergent.
Yes.
So you have to regulate it. Yes. But for 6-point, the triangle is finite.
Yes.
So for n-point, you get some massive n½ gone.
Yes.
So that is also finite. And the integrals over P are always producing finite functions,
yes,
or not?
Yes.
Okay.
The integrals over P, at least for the triangle and box that we've analyzed, it seems to produce finite terms numerically. Whether or not we can perform it analytically, it's not yet explored.
Okay, thank you.
Another question.
Yeah, just a quick question. Can you see this happening from the Schwinger-Keldysh propagators perspective?
Not directly. The thing is, you have to add everything in Schwinger-Keldysh to get this. So it's not something that exists for any individual term, but it's the structure only comes up once you add everything.
Okay, thanks.
Had many nice questions. Let's thank Chandramouli again.